So let's go through the final exam review for spring scales. The first problem says you're standing motionless on a spring scale but are now jumping upwards. The spring scale reads more than your true weight as you jump because, one, you weigh more than you were when you were moving upwards. Two, it is pushing up on you harder than you are pushing down on it. Three, you are accelerating downward into its surface. Four, it is pushing on you with a force greater than your weight. And as always, the first thing to do is to try to eliminate things. And clearly, um, the the first thing that you can say is that clearly your weight doesn't change as you move upwards into the air. And the second one says it's pushing up on you harder than you're pushing down on it. That really kind of indicates that the force which you are applying to the scale is somehow different than the force that the scale is applying on you, and that can't be from Newton's third law. So you can eliminate that one. Clearly you're not accelerating downward to its surface because you're jumping up into the air, so you can get rid of that. So this one's really the only one that makes any sense. And again, the idea is that if you're standing on a scale, you still have your weight down, that's the force on you, and the scale is pushing up on you. Normally these are equal to each other, and so you're just standing stably, and so then the scale reads properly. But in certain cases, if you're jumping upwards, then the force upwards is larger than your weight, and so then you accelerate upwards. And again, what the scale is reading is essentially the force that you are applying to the scale, which is essentially, this is the Newton's third law of pair to the force that the scale applies onto you. And these have to be equal to each other. So the idea is that if as you apply a larger force to the scale reads more, and so then you go up into the air because now the scale applies a larger force to you. Okay, so let's go to the second one. You've always wondered how much one of your friends weighs and devised a scheme to measure his weight accurately. You have him sit in a tubular steel chair. This popular style chair consists of a single steel tube that is bent into a frame and that supports a seat bottom and a back. The empty chair weighs 10 pounds and is 30 inches tall. The frame acts as a spring and bends downward slightly when the chair is occupied. When you sit properly in the chair yourself, it bends downward 1 inch. When your friend sits properly in the chair, it bends downward 2 inches. From that observation, you know that your friend's weight is about 1/2 as much as you do, twice as much as you do, 4 times, 1/3 as much. And again, the picture in your head is that this is the kind of chair that has, it's bent into a shape. And so the idea is that as you sit in the chair, you apply a larger force down the chair, and so therefore the chair, bends downward. And the larger that force that you apply to the chair, then the more it bends downwards. And so again, this is, Hooke's law, which basically says that for a spring, the force is proportional to the displacement. So if it displaces twice as much, then clearly the only answer is that it weighs twice as much as you do. Clearly, these wouldn't work either. You could eliminate those because clearly it doesn't weigh less than you do, and it would bend more. Okay, last one. Okay, a 2 kilogram hanging plant's being held up by a spring. The spring stretches 10 centimeters from its equilibrium length. If you now add 1 kilogram of water to the plant's pot, how far will the spring be stretched from its equilibrium length? So again, you imagine that you have some sort of a ceiling, and you've got a spring kind of thing hanging down from the ceiling. When you hang a plant from it, which has a 2 kilogram mass, then it stretches out. The plant's hanging there. And so the idea is it stretches 10 centimeters. But this is to give you that 2 kilogram mass for its appropriate weight, which is about 20 newtons. So if you add another kilogram of mass, then clearly if 10 centimeters is required for 2 kilograms, then for 3 kilograms it would have to go another half again as much. And so it will basically just stretch a little bit more, 15 centimeters from its originally height. And so clearly this is the only appropriate one. So that ends the discussion about the problems that are on spring scales. The main thing to remember in this is that when a spring scale, two things. One is as a spring gets displaced, stretched out, if you double the length, you double the force that's being applied. On the other hand, if you displace it from equilibrium, it oscillates basically away from equilibrium until it eventually settles down.